Hi, everybody. Welcome to our TAC Talk for today, Tuesday, December 3rd. Happy Thanksgiving to all of you. We did have Thanksgiving weekend this last weekend, so it was amazing. And hope you got to enjoy with your friends and family. And thank you for all the projects that come to Linux Foundation. And thank you to all of our audience who participate in it. Without you, we cannot do it. Hope our tech sessions lead the way as a guidance for you to learn about our projects. Today we have an amazing guest on our tech talk, and these tech talks happen bi-weekly on Tuesdays. So if you ever miss a tech talk, we have it posted on our LinkedIn and YouTube channels. And I am the host of TAC Talks, chair of Technical Advisory Council at Linux Foundation AI and Data. Today on the Tech Talk, we have Romeo from IBM, and he's going to show a cool project, a cool open source project that is also being used in IBM and several other companies. So, Romeo, why don't you introduce yourself?
Okay, hey, thanks for having me. So I'm Romeo. I'm working for IBM Research in the Zurich lab in Switzerland, which is part of a multinational research organization of IBM. So we do the latest and greatest things in quantum computing and many other things like the latest and greatest AI processors. So a lot of cool people are working there, and I'm working there as a software engineer. And basically my core knowledge is about infrastructure, open source infrastructure for data and AI processing all around. Torch and also automation and parallel computing.
That's amazing, Romeo. So we have like an amazing talent represented here who is going to walk us through the an open source project. Thank you, Romeo. So let's start with like what is claimed and what was the motivation behind starting the project. If you can guide us through that. Yeah,
Mhm. Okay, so let me actually share my screen
sure.
and let me show you how all began. So I was working for an open source department in San Francisco that created contributions to Apache Spark and Torch and Kubernetes and Kubeflow. And there was another project which is called Elira, which is also part of the Linux Foundation AI, and which we already got into an open source, open community governed project in LFAI before we did this for Claimed. And the idea behind Elira is you have a Jupyter Lab extension or some Jupyter Lab extensions. And what you see here is a drag and drop editor where you can drag and drop Python scripts and notebooks and R scripts and shell scripts to a canvas. Also, that canvas system is open source. It's called Elira Canvas. It's a React-based library, and you can connect those boxes, and then you can just click run, and you can run them locally on Kubeflow or on Airflow. And the idea is everything what you coded up here is then transferred to the cluster and executed there. So that's an easy way to create pipelines for Kubeflow and Airflow. And then I just had the idea, okay, since we have such a cool tool to drag and drop any code snippet to a canvas and create a pipeline within seconds, one thing is missing, and that's a library of those code snippets and notebooks. So initially, the whole project started as a component library, which we called Claimed, just to have all the buzzwords in it, a component library for AI, machine learning, ETL, and data science, just to be sure that we cover everything, no? And then the idea is you create a notebook and or a Python script or a R script, and then you run a compiler, and that compiler creates a container for you, and plus the container, it creates deployment descriptors for the target runtime. So let me actually show that to you in 2, 3 slides.
Sounds good.
Okay, so in our department, so I'm working for the IBM Sustainability Software Department. It's all around data management and foundation models for weather and climate and Earth observation data. And we shuffle around terabytes and even petabytes of data. And to streamline this process, we are using a tool called Kubeflow, which runs on top of Kubernetes. And that allows you to just create pipelines like this, and the actual pipeline components, they are created by Claimed. So the way this works is you have on the left-hand side, you have Python scripts and R scripts and notebooks, and then you trigger the compiler, and the compiler creates for you KFP components, Kubernetes jobs, and common workflow language tasks, and you can also now run them on Slurm and other workflow management systems. Okay, and how this looks like is you have here, for example, a data scientist. He's good in pre-processing data using Python. And then you have a researcher. He's good in writing some analytics in R, although everybody hates R in my environment, but still we needed to support it because some researchers wrote some R code. So actually the compiler also supports R. And you see the blue thing is something which is taken from the left-hand side, and the green things are auto-generated by the compiler. So the first thing it creates is a Docker file. And that Docker file contains basically instructions to build a container image, which contains this source code plus all the dependencies. That is automatically generated and pushed to the target repository if you like to have it pushed. No? Otherwise, it's just generated locally. And then we also auto-generate for the different downstream execution environments the deployment descriptor files. So if you use CWL, Common Workflow Language, we auto-generate the CWL tasks. If you are using plain old Kubernetes jobs, we are creating the CWL, sorry, the Kubernetes job YAML. And if you're using Kubeflow, we are generating the KFP component YAML. And that way you can concentrate on this left-hand side, and everything on the right-hand side is automatically done. So before I continue, I will show you the contents of the library.
So I have a
And
quick
yeah,
question. In the previous screen, you showed the Docker file and the bunch of like binaries that get added in
yes,
the claimed operator, right?
yeah.
So is this like a orchestration tool, like automated orchestration library for your data pipeline that is being managed by Airflow, or like
Yeah,
how
so
would I?
so this tool is meant to create the individual processing steps, because the normal way you would create a Kubeflow pipeline component, so one individual processing step in the Kubeflow pipeline is you write the code and you
Mhm.
write a Docker file, and then with that you create the container image, and then you write the KFP component YAML file, and that is all taken care of for you. In the KFP YAML file, for example, have a look. I'm just starting here to walk you through. Anyway, so so you see here, this is a KFP YAML file. No, this is something you normally code by hand, and you need to take care of defining all the inputs and outputs, and also the data types, and whether it's optional or not. And also you need to then to pass all those parameters to your script, and all these things are very error prone and tedious because it involves a lot of copy pasting and making sure, for example, this term here, this string matches this string, and if you do something wrong, it fails after you initiated the pipeline. And we thought that's just stupid stuff which can be automated, and that's what Claim basically does, apart
Got
from
it.
the parallel computing part, but I can show you that later.
Got it.
Mhm.
Thank you.
Okay. So if we now have a look at how to create the claim component, and it's also like the Java slogan, no? You write it once and it runs everywhere, and the same idea we have here. But in this case, we are obviously not running on top of a JVM. We are running on top of any workflow execution engine. and initially claimed was containerized only. So we supported Docker, we supported Docker Compose, and then Kubeflow and Kubernetes and all those things. But the latest version also has the capability of creating containerless components. I'm just giving you here a little excursion to that functionality. So if you want to run, for example, on an HPC cluster, that was a recent requirement we got from IBM Research, because we are like partnering with a lot of large organizations like NASA and ESA and YLR and so on, and Research Center Nülich. So they have supercomputers and they don't have any containerization. So what we did is we have a containerless mode for claimed now. And the way this works is it creates the environment as a folder and packages the folder, the environment folder, plus the code into one zip file, and that's then a portable component. There's only one downside of this way of doing it, because if you're containerized, you can specify the base image. So if you have some weird C++ libraries your Python code needs, in the containerized version of the claimed compiler, it's easy to just use a base image which contains all those weird C++ libraries, and you can just make use of them from Python. But that functionality you don't have. So that means if you use the containerless mode, you need to make sure those weird C++ libraries are pre-installed on the target system. That's the only caveat. Okay, so let's have a look at one easy component. It's like a Hello World component. So if you create a pipeline, you might want to pull data from a HTTP source, and that is just the code doing it. And to have a claim component operational, there are 4 things you need to follow. The first is you need to specify a description. 1 second. 1 second. Du musst raus, Schatz. Ich habe wirklich keine Zeit. Geh raus.
I think they also want to present. He's presenting some amazing, cool stuff. Yeah, so that's the claimed. Real quick reminder, if you have questions about claimed, please definitely comment on our LinkedIn and YouTube channels so that we can answer it live. And if you're tuning in, we are covering our open source project claimed. So yeah.
Sorry.
No.
Okay. Okay. I was here. Okay. So you need to specify the description, and then the next thing is obviously you need to specify what dependencies your code has. In a Jupyter notebook, this is easy. You can also add this in the Python script at the beginning. And what then the compiler does, it pre-installs those requirements. And some people like to use requirement.txt files. That's also possible. You just say pip install -r requirements.txt, and it's also working. Then you have the imports, obviously, because some linters, they require that the imports are at the beginning of the file. And then the most important part is this here. So that's how you get in the parameters into your code. And the way it is done is it reads environment variables. And here you can already see that you can have either mandatory fields. So for example, URL is a mandatory field. And then you can have optional fields. So if you have a default for your parameter, then it becomes an optional field, and that gets also reflected in the KFP YAML, because then it's marked as optional. And the last thing which you don't see is you can cast. So you can cast such a parameter to integer, float, or boolean. And then automatically in the YAML file, we will reflect this and mark this parameter as a boolean. And then there's just the code you write here. That's all you need to do. And then it will automatically work. Okay, so this is one example of such a component. Let's have another one. That's the most used one. Let's actually go. So you see here are all the categories. No, we have analyze, anomaly detection, checkpointing, automatic deployment of models, for example, filtering components if you want to filter out by predicate, some geospatial components, the input folder I already showed you, monitoring, NLP. Output is everything writing to somewhere, no, writing to a object store or writing to a database. We have some inference components. And then here in the utility section, that's the one people I think use most of the time. This is a cost utility. It's relatively simple, but the reason why people love it is we have here the possibility to sync. People can sync data from their local clusters to a COS backend or vice versa. And it's very easy to install, because one thing I didn't mention is Claimed has a CLI, a command line interface. We will see that later. So whenever you create a Claimed component, obviously you can use it on Slurm, on PBS, on LSF, on Kubeflow, Airflow, Kubernetes, Docker, wherever you like, also containerless. But also it has the CLI. So you can say claimed space, component name space, and the parameters, and then it just becomes an ordinary command you can use on any system. Okay, so that's also the implementation of the component. And you see here, that's an example for a Python file, which turns into a component. And you see here the dependencies you can also just define like you have in this comment. And again, if the requirements are in a requirements.txt file, you can say in this line pip install -r requirements.txt. It will also work. Okay, enough talking. Now let's actually code something. If there are no questions in the
Yes.
meanwhile.
Please go ahead. Yes. So
Okay.
far, so good, Romeo.
Okay. Okay. Before I code something, I want to show you something. What I code. I just forgot to mention that. So let's start from this slide. So it's nice to have a framework which just takes a bunch of code and makes it run everywhere. That's already nice. But the problem is if you have a lot of data. So, for example, we have hundred thousands of files which we need to process individually. In our case, we have a lot, for example, satellite images, and there is some cloud removal algorithm which removes clouds from those images by some intelligent means. So we need to apply this or some atmospheric correction or anything you can imagine. Some operation you need to apply on each file, and you have 100,000 files. Obviously, if you just loop over it, you have 100,000 loop iterations, and it will just occupy whatever one machine, or if it's even worse, maybe only one core. So wouldn't it be cool to just easily have your code running in parallel without you doing anything? And that's something we just built into the compiler. Since we anyway generate code, we obviously can also generate any code we think is necessary to allow for easy parallel processing. And what we do is we have, like every parallel or grid computing system, there needs to be some coordinator. The problem is the coordinator is often hard to set up. Also, network-wise, not everybody needs to have access to the coordinator, and sometimes this is on a firewall and network basis relatively complex. So the idea is here we ingest or auto-generate the coordinator code into the component itself. So each worker, so each claimed component becomes a claimed or grid computing worker. And then the coordinator code is auto-generated into that worker. And the only thing the coordinator needs is one central file system or one central database. And the file system you can choose between a cluster file system. So if you are on a high performance computing environment, we just have some mounted path which we use for coordination. And if we are in the cloud, we use Cloud Object Store S3 for coordination. The cool thing is it costs nothing, no? Because S3 or Cloud Object Store is super cheap and it's super reliable. It's not really fast, but for that we don't care, no? And that way you can run the workers all over the world in a hybrid environment. Some workers can run on a HPC cluster containerless. Some workers can run on a laptop. Some workers can run on a GPU cluster. Some workers can run on an OpenShift or on a Kubernetes cluster. They all, through the injected code, connect to the coordinator, or let's say connect to the coordinator data backend. The coordinator runs obviously in the workers, but the data backend. So it's either a database or it's a file system, S3 or a mounted file system. And the coordinator does nothing else than for each tasks writing a set of files. So if it takes a file. If one worker takes a file, it locks the file. And when the worker is done, it deletes that log file and marks this file as processed. So this file will never ever get into another worker. And in case a worker crashes, the coordinator we compile into the workers automatically takes care of the crashed workers. So there are some locked files from the crashed workers, and if they are older than a specified number of seconds or minutes, then we just delete them. Okay, so that way we can create a globally distributed grid computing environment just by writing 2 lines of code and executing the compiler. So let me
That's
actually show
amazing.
that to you. Okay,
Yeah.
so I have already prepared that.
It looks like for existing files and existing processes, it can also help optimize a lot of workloads if it can automate some of the processing, like you mentioned.
Yeah, so for example, we have now someone requested us to ingest some satellite data set, which was quite huge. And
Mm.
we started this last week on Friday. And then just we had a cluster which has 12,000 CPU cores. And we just could run like 8,000 parallel processes without any problem. No, so we can just push down the number of days we need to process by just adding. So it scales linearly, basically. No? It's an easy operation. If you're familiar with MapReduce, it's basically the map part. So we don't support aggregations, but you can like address a lot of problems with that just simple map pattern. And so you can maybe think of it like a MapReduce framework without the reduce, but you are not limited to the MapReduce framework. So for example, if you would consider Spark or Hadoop, you are like tied to this platform. No, every map operation needs to be implemented in the programming language and API the framework supports. In our case, a map function can be any arbitrary Python or R or shell script code. And I think that that's a real advantage. Okay, let's have a look how easy it is to create such a parallel function. So we have here a Python file, and you see there are just 2 lines of code. First is the function definition. So we call this grid process. That's the default name. You can also change it and pass it as a compiler argument. And then it will obviously call the other function if you don't like the function name grid process. And then the first parameter, it's also something you can choose. You can choose a task ID or file name, or you can just choose it to be a Python dictionary, whatever. Because sometimes task descriptions are more complex than a single string. And obviously, it's nice you just accept the Python dictionary. And then the only thing, so that's your implementation. And obviously, in this case, it's just printing out the task ID. But now you can imagine, since you have the file name or some more complex dictionary describing the task, you know where you, for example, need to pull the data from, what you need to do with the data, and then where you should push the data to. And then everything is handled by the coordinator, which gets compiled into that component. So let's actually do that. I just ran this before, but let me actually run it again. And I didn't try to run it again, so I hope I'm not messing up something. But see, that's here the relatively simple command. No, it's okay. The first command is you create, or the first thing you do is you create a Python environment, which I'm already in. Then you say pip install claimed, and the third thing you do is you say C3 for the claimed component compiler. You say create grid wrapper, and then this Python file I've shown you. By the way, if you want to create an ordinary claimed component, you say C3 create operator. But in case we have time, I will show this to you quickly. But this one is obviously a little more complex from what it does behind the scenes. But let's actually run it. And it will, since it's now creating a containerized version of it, it will use Docker in the background, or in this case, this is Fedora, it's using Podman to create the container image. And it will also tell you how you would run this component it created using the claimed CLI. So in order for this to work, you can either scan a directory for files, and then each file becomes one task, Or what I did in this case, I have just created a file called test CSV. And that test CSV contains all the tasks. If we have now a look at the test CSV file, you see here the first is the column name, that's optional. And then we have file 1 and file 2. So this is basically just a job with 2 tasks. And let me actually get rid of the processed files. That's just an artifact from the previous run. So we have only this test CSV in the folder. And by the way, we can specify multiple backends when we create. So if we run this command create grid wrapper, it's using the default backend. The default backend for the coordinator is just using a local file storage. There are different backends you can specify. Another one is, for example, using S3 or COS file storage. Then all those coordination files are in a COS bucket, or you can use a database. But for simplicity, let's use this one first. So, and then what I need to do is I can just run this. So this is now how you would execute this locally. So you have here claimed. This is the CLI to start it. Then you have here dash dash component. That's the component you just created. No, that's the grid wrapper, because it derived the name from the Python script because it was called gridwrapper.py. It takes care of versioning. So you can auto increment the versions. Then that's the log level, which there's some automatic logging going on, and you can set a log level to be reported. And then what we have here is that's the file containing the tasks. So you can either specify the CSV file containing the tasks, or you can specify a folder, and then each file in that folder becomes one task. And then if you are using the CSV file, you specify if you have a column name, that's here file name. And then you need to specify where it should put the files to coordinate the work. So in that folder, the files like filename.log and filename.processed are generated, just to make sure that the workers are not processing the data multiple times. Here's the log timeout. So if a worker crashes after 10,800 seconds, that's obviously for larger jobs, it gets deleted and reprocessed. And also in case of an error, no, you can try, you can recover from errors if you're lucky. If not, then obviously you need to fix your code. Then that's so we can keep the errors if you like. Then all the standard out and standard error would be captured into that file. And then another thing is staggering start. It's 0. That means if you have like 10,000 workers and all the workers are attacking the coordinator path at the same time, that will become a bottleneck. So we randomly can staggering start the individual workers by a number of seconds. And that way, not all the workers are accessing that coordinator folder at the same time. So let's actually run this. So it's obviously already done. And you see here, 2 files have been processed, 0 errors, 0 logged, and 2 in total. And though that function has been executed, we see it here, it just echoes or prints the task ID or file name. And then what we also see in the temp folder, the coordinator has written those 2 files. So during processing, there has been a file.text.logged and a file 2.text.logged, and those have been deleted since the task has been completed, and then they are just marked as processed. And if you rerun this, it won't get processed anymore. Okay, I think that was like a perfect timing. So are there any questions, additions, comments, complaints?
No, this was amazing, Romeo. Thank you for walking us through the code. It was very simple to run. So I imagine this was run on like a smaller set of file for demo purposes.
Yeah,
For I'm
only 2, yeah.
like, yeah, I'm curious if you have to run for like large amounts of file. How does the processing work? Like, does it constrain on the timing processing? Yeah.
Yeah. Okay. So, as I said, we have at the moment 100,000 files to process, and maybe it's already finished. I obviously for data protection reasons I cannot show you your our internal system, but we have started it last week on Friday, and I think it was completed on Monday. So we ran 8,000 workers in parallel,
Mhm.
and in that instance, we use a relational database for the coordination. It would work for the actual processing, but the problem is if of those 100,000 tasks, some tasks are failing, and you want to do some analytics of how many have failed and why. It's much faster to just ask a database via a query, or we also have a Grafana dashboard on top of the database, rather than like with LS and filter and grep and AWK and so on, finding out what's going on. That's the only reason. No, for analytics purposes, it's more easy to just run the queries on top of a database.
Got it, got it. And I'm curious, like, who else is running this library except IBM?
Okay.
What are the use cases? Yeah.
Okay. I don't know who is running it at the moment, but we have a list of companies who already ran it. And
Mhm.
that's, for example, Novartis and JP Morgan Chase and University Hospital of Basel and Red Hat and some other smaller companies.
Got it, got it. And Romeo, usually, I ask this question for our audience because they are trying to build something, and sometimes, existing use cases can serve as a inspiration for them. So, like you mentioned, all these companies, where can we find the use cases? Do you have like any blogs where they talk about it, or like
Okay,
anywhere?
we have a website which is called claimed framework dot. I have to double check actually.
That would be great. Yes.
Let me just double check on the name. Is it acclaimedframework.github.io? That's where we put stuff. And I have a lot of stuff in my private YouTube channel. I'm more like a bit of a YouTube guy. Let's see if you can see that here. Yeah. So if you go to videos and search for claimed, you will see a lot of claimed videos.
I see. We are talking to a YouTuber now.
I think so. And yeah, so it's not so much about use cases, or you can think of whenever you cannot do it with SQL, like one of those parallel SQL frameworks like Presto or Impala or Spark SQL, because you're too limited, because your data doesn't fit in the tabular scheme, you can use this library. No? It supports everything Python and R and shell scripts and C libraries are supporting. So you can use it. We use it a lot for images and climate data. You can use it for video, even for text. Yeah, it's flexible in that sense.
That's awesome. And are there any community events that happen that you claimed project hosts?
Yeah. Okay. I mean, we have a weekly community call. Feel free to join. I think it's you can find it via the LFAI. And I think the
Okay.
next is even happening maybe next Friday or next Friday in a week.
Got it. Got it. Thank you so much. Any other information you would like to share, Romeo, as a closing thought?
Mm, yeah, I think the next step I want to look into is if it would be possible to do hybrid parallel deep learning model training, because this library can actually run globally distributed on different locations, and it's maybe a nice thing for something like federated training, where we have different data centers and they have access to only partitions of data, and that way we can train a neural network using some federated learning approach. And I think this library would be a nice way to test whether it's possible to do so. Still there?
Oh yeah, sorry. I was
Ah.
all talking on mute. Okay. I was saying thank you so much. Yes, I pasted the link in our chat. And yeah, if anybody has any questions, definitely reach out to Romeo, or also on the project. There is GitHub mentioned, so you can post your questions on GitHub and check it out. You can also, like, post your questions on our live channel too. Romeo, I was asking if you have any other closing thoughts.
No, that's all. Yeah. Thank you.
Awesome. Yeah, with that, I think, yeah, today we presented Claimed by Romeo from IBM research team. And he basically gave a lot of technical information. So take your time, feel free to, watch our video if you missed it. It will be recorded and posted on LinkedIn and YouTube channels. Again, thank you so much, Romeo, for presenting today and being our guest on TAC Talks. It was super great having you. And to the audience, I think we are going to be hitting next TAC Talks on Christmas. So maybe this is our last TAC Talk of the year. Um, so yeah, with that, if anything comes, oh, we have one more. Okay, we have one more. My thank you, Carly. We have one more on December 17th that will be posted. Information will be posted on our LinkedIn channel, so feel free to join that one. And then yeah, I will wish you Christmas on that tech talk. Anyways, thank you all for joining, and wish you a very good week. Yeah, see you on
Okay, and the
next.
tech talk basically is done by some friends of mine, so we are all
Oh,
one community.
yes, yes, yes. That's awesome. That's awesome. All right. With that, let's sign off. And thank you all for joining and listening to our Tech Talk.
Thank you.
Adios.